And now everybody to the dance floor.
Rolling my sleeves up the hair to make you smile, yeah. Girl, I've been hitting that graveyard shift. You will find another one built for this dirty work, dirty work. Baby, I don't need no help. I do it all by myself. Girl, I've been putting in overtime. You ain't gotta tell me what's on your mind. Dirty work, dirty work. Cause when you do what you love, you're gonna love what you do. You know I do it with love. Each night I do it for you. It's the dirty work. Somebody's gotta do it. Dirty work. So we're getting into it. Dirty work. Go and put your body through it. You know it ain't no 9 to 5. We going sundown to sunrise. Dirty work. Dirty work. I'm filthy down to the core. Leave all your stress at the door. You know you need to stop scrubbing with Mr. Clean. Bring it right here, come next to me. Dirty work, dirty work. Cause when you do what you love, you're gonna love what you do. You know I do it with love. Each night I do it for you. It's the dirty work. Somebody's gotta do it. Somebody's gotta do it. Dirty work. So we're getting into it. Dirty work. Dirty work. Go and put your body through it. You know it ain't no 9 to 5. We going sundown to sunrise. Dirty work. Dirty work. Cause when you do what you love, you're gonna love what you do. You know I'll do it with love every time I'm with you. It's the dirty work. It's the dirty work. Somebody's gotta do it. Somebody's gotta do it. Dirty work. So we're getting into it. Dirty work. Dirty work. Go and put your body through it. You know it ain't no 9 to 5. We going sundown to
This lecture will learn the basics of oceanography. Let's get started with this question. How do ocean currents work? When we learn physics of ocean currents on some textbook, there are many equations, and we couldn't sometimes understand what they mean. That's the same for me. So I find an interesting story on ocean currents. Let me introduce the story. In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed over the board, and the waves swept 28,000 rubber decks. So what do you think happened after? The decks have since washed up all over the world, and researchers have used their passes to chart a better understanding of ocean currents. So let's think about driving forces of ocean currents. Ocean currents are driven by many forces. First, you can come up surface wind stories. Wind drags the ocean surface. How about tide? Tide can change the direction of ocean current, especially for the coastal area. Of course, we need to think about water density depending on water temperature and salinity. If we have higher temperature and smaller amount of salt, water density should be lighter and it comes up to the surface. If we have lower temperature and larger amount of salt, water density should be heavier and it goes down. The last one is the rotation of the Earth, called the Coriolis effect. In addition, the topography of the ocean floor and shoreline modifies those motions. Topography is causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind the surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the below layers. In fact, water as deep as 400 meters is still affected by the wind at the ocean surface. Here, let's make an equation for the momentum between the atmosphere and ocean surfaces. Now you have the surface wind speed of 10 meters per second, the atmospheric density, seawater density, duration, and momentum exchange coefficients that depends on the surface roughness. The relation of each momentum would be like this, and you can estimate ocean surface current speed. If we zoom out to look at the patterns of surface currents all over the Earth, you will see that they form big groups called gyres, which travel clockwise in the northern hemisphere and counter-clockwise in the southern hemisphere. There are 5 major gyres of the Indian Ocean Gyre, North Pacific Gyre, South Pacific Gyre, North Atlantic Gyre, and South Atlantic Gyre. If you zoom in to look at the patterns of surface currents, you will see that there are a lot of eddies. When we focus on the Indonesian Sea, one of the most famous eddies is the Halmahera eddy. Actually, I visited Ternate in the last week. There is a Sultan kingdom started from 12th century, and I am very surprised at the fact that they have a historical map drawing the Halmahera eddy in 16th century. I can see that they had a fairly advanced understanding of oceanography. By the way, if the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the south pole to the equator is deflected eastward, so that the major streams of wind form loop-like patterns along the ocean basins. This is called the Coriolis effect. The Coriolis force is an apparent force that changes the direction of flows, and it increases with the higher latitude. The Coriolis force is represented by these equations. A zonal component is in proportion to a meridional motion, and the meridional component is in proportion to a zonal motion. Unlike surface currents, deep ocean currents are driven preliminarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called a Thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the Global Conveyor Belt. In addition, we have specific surface currents like this. For example, along the eastern coast of Japan, we have Kuroshio and Oyashio currents that are the western boundary currents. Over the equator, there are the equatorial currents that are predominantly driven by the wind, and they are accompanied by the equatorial counter currents. All they have a wide range of variations in response to atmospheric variations. That's why we need to observe their actual status. Then, how can we observe the ocean? We can bring a thermometer by a ship, and we get a profile if it sinks to the bottom. If you like to get profiles repeatedly, you can put a wire on the thermometer. The most famous one is CTD observation to monitor the basic status of seawater. We did this operation 8 times per day on the RV Mirai during the YMC campaign. Another is microstructure profiler to see more precise turbulence of seawater. If you want to continuously monitor ocean profile for a longer period, you can use a float connected by a wire to sinker. That is, Triton V observation. We deployed new one, replacing old one every a few years at fixed points. Recently, a persistent mobile data gathering platform is developed. That is called Waveglider. In addition, if you did radius on the operation, you could understand air-sea interaction processes. RV Mirai has an automatic launching system for radiosonde like this. We did 8 times per day just before CTD operation. Now you can get on RV Mirai by 360-degree virtual tour. In this way, we did observational campaigns. Let me introduce some examples from the Pre-YMC in 2015 and YMC in 2017. General features during the two campaigns are these. In 2015, we did before the MJO passage, under the situation of the weak easterly wind less than 5 meters per second, and sea surface temperature is more than 30 degrees Celsius. On the contrary, in 2017, we did after the MJO passage, under the situation of strong westerly winds more than 10 meters per second, and sea surface temperature is less than 29 degrees Celsius. And as for the ocean structure, we observed hairline in 2015, and we observed eddies in 2017. I am very interested in the fact that the eddies has the vertical motion in the mixed layer, and such motion could increase salinity near the surface. Looking at time depth sections of temperature in 2015 and 17, they are entirely different. Look at the mixed layer by the dashed lines. The mixed layer depth in 2015 is very shallow, less than 20 meters, but that in 2017 is more than 100 meters. Even a very precise ocean model cannot exactly represent this kind of fine surface structure, and we need more observations. Though we have oceanic objective analysis products, we can improve them after the observations are much more sufficiently assimilated. Looking at salinity sections, we have a very strong salinity stratification in 2015 because the small salinity near the skin surface due to the large amount of diurnal rainfall. On the contrary, we have well-mixed salinity, 200 meter depths in 2017, and drastic increase of salinity from underneath is shown in the latter half. At the same time, we have a drastic increase of turbulence from underneath in 2017. In contrast, the turbulence below 50 meter depths in 2015 is much smaller than in 2017. Looking at current direction, you can see a steady southward flow by warmer colors in 2015 and rotational flow showing striped cold and warm colors pattern in 2017. That is, there is a longshore flow under the weak wind situation before the MJO in 2015, but there is a longshore eddies under the strong wind situation after the MJO in 2017. Such different features of the ocean currents to the west of Sumatra are made from these different atmospheric features and also reversely feedback to the atmosphere. That's why we need your love more and more. Thank you for coming to Japan and looking forward to seeing you again. Goodbye!